analyzing the amplitude of the parameter by means of regularization. We'll explore this idea in this video. In regularized least squares, we consider the loss function the norm of y minus pi theta squared plus lambda norm of theta squared, which we minimize with respect to theta. Here the first term is called the data fit term, or the misfit term, and it's proportional to the negative log likelihood. The second term is called the regularizer, and the regularization parameter, lambda greater or equal to 0, controls the strictness of the regularization. Here we note that we're using the 2 norm, or the Euclidean norm, but we could just as easily use any other p norm. For p equals 1, the regularizer is called lasso, least absolute shrinkage and selection operator. Regularizer, lambda norm of theta squared, can be interpreted as the negative log Gaussian prior, which is used in the map estimation. More specifically, with the Gaussian prior, probability of theta being normally distributed with mean 0 and variance b squared I, we obtain the negative log Gaussian prior, negative log p of theta equals 1 over 2b squared norm of theta squared plus a constant, so that for lambda equals 1 over 2b squared, the regularization term and the negative log Gaussian prior are identical. Given the regularized least squares loss function, it consists of terms that are closely related to the negative log likelihood plus a negative log prior, it's not surprising that when we minimize this loss, we obtain a solution that closely resembles the map estimate. More specifically, minimizing the regularized least squares loss function yields theta RLS, which is equal to phi transpose phi plus lambda I inverse phi transpose y, which is identical to the map estimate for lambda equals sigma squared over b squared, where sigma squared is the noise variance and b squared is the variance of the Gaussian prior, p of theta. So far, we've covered parameter estimation using maximum likelihood and map estimation. We found point estimates theta star that optimize an objective function, a likelihood or posterior. We saw that both maximum likelihood and map estimation can lead to overfitting. In the next video, we'll discuss Bayesian linear regression, where we use Bayesian inference to find a posterior distribution over the unknown parameters, which we subsequently use to make predictions. More specifically, for predictions, we will average over all plausible sets of parameters instead of focusing on a point estimate.